Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya. Hello everyone, I am Andi Ammar Akrar from State University of Makassar. In this video, I will explain the implementation of pure mathematics in other fields, or specifically in the field of biology. The topic that I will present in this video is the application of matrix diagonalization to genetic inheritance. Very interesting, isn't it? So, if you want to know well about the topic, make sure to watch the video till the end. And yeah, let's go to the video. In mathematics, one of the topics of algebra that may be familiar to us is matrices. Matrix theory is one of the branches of linear algebra, which is an important discussion. In line with the development of science, the application of matrices has been widely used found in other fields, such as economics, physics, computers, and also biology. One of the biological problems that can be solved with the matrices is the genetic problem. Genetics is a branch of biology that studies heredity, namely the passing of traits from one generation to the next. In the field of genetics, the problem found is to find out a superior individual from several generations by doing continuous crosses. If done conventionally, it will take quite a long time if the species is classified as rare. This problem can be solved by analyzing the diagonalization of the matrix based on the genotype probability of the parent. The formula used to investigate genetic inheritance is D equals P inverse AP, where D is the diagonalization of the matrix, A is the matrix obtained from the cross probability table, P is the matrix which is formed from the eigenvectors of A, and P inverse is the inverse of the matrix P. To investigate the application of matrix diagonalization to genetic inheritance up to the nth generation, we use the following solving steps. The first one, form a linear equation from a table that describes the probability of each genotype so that an equation is obtained in matrix notation. Form a matrix A, then look for the eigenvalues of matrix A so that the eigenvectors corresponding to the eigenvalues are obtained. Form a matrix P of eigenvectors corresponding to their eigenvalues. Substituting matrix A with matrix D, which has already been diagonalized by P. Solve the genotypic distribution equation in the nth generation. Forming an explicit equation. And last one, find the limit of each equation for n to infinity. In autosomal inheritance, an individual inherits one allele from each pair of alleles of its parent to form its own pair of alleles. For example, if a parent has the genotype capital A small a for a particular trait, the offspring will inherit the capital A allele or the small a allele from the parent with equal chance. The controlled cross is a cross between a normal individual with all possible genotype, which are as follows. To calculate the probability of a gene belonging to an individual, we can create an x to the power of n matrix with 9 rows and 1 column, where an represents the probability of an individual with the capital A, capital A, capital B genotype in the nth generation. Bn represents the probability of an individual with the capital A, capital A, capital B, small b genotype in the nth generation, and so on. From the previous table, it can be determined the genotypic distribution of each generation from the genotypic distribution of the previous generation using the following 9 equations, where the equation sets all the resulting derivative, namely AN, BN, CN, and so on, which are expressed by AN-1, BN-1, CN-1, and so on, while the coefficients of the 9 equations are derived from the genotype probabilities that may be owned by the individual from the cross. Now we can express the 9 equation in matrix notation as x to the power of n equals a times x to the power of n minus 1. And you can see the x to the power of n and a matrices on the screen. Through some algebraic process, the formula can be declared as x to the power of n equals a to the power of n times x to the power of 0. But before determining x to the power of n, we must first find a to the power of n with the diagonalization formula. A to the power of n equals p inverse times d to the power of n times p. To diagonalize A, we first find the eigenvalues, and you can see the process. We get the eigenvalues of 1, 1 over 2, 1 over 4, and 0. For lambda equals 1, we substitute the value of lambda on the lambda I minus A matrix. Then, by elementary row operations, we form it so that it becomes a row echelon matrix. From the row echelon matrix that has been obtained, then we create a suitable system of equations that can be seen on the screen. And we get the basis for the eigenspace for lambda equals 1. The same process we do for lambda equals 1 over 2, lambda equals 1 over 4, and lambda equals 0. The process and result are as follows. There are 9 basis vectors in total, so the matrix can be diagonalized. The 9 basis vectors are formed into the P matrix. After obtaining the P matrix, then we can determine the inverse of the P by reducing the matrix to identity matrix. And you can see for the P and P inverse. After obtaining the matrix A, P, and P inverse, we can determine D by the formula D equals P inverse times A times P. Now you can see the matrix D that we have obtained. Based on the equation A to the power of n is equal to P inverse times D to the power of n times P, we get x to the power of n is equal to a to the power of n times x to the power of 0. By substituting the value for a to the power of n, we get x to the power of n is equal to P inverse times D to the power of n times P times x to the power of 0. After doing the multiplication process, now we can see the results for the x to the power of n. For the x to the power of n matrix that has been obtained previously, explicit equations can be made for the fractions of the 9 genotypes in the nth generation in terms of the initial genotype fractions. You can see the equation for AN, BN, CN, and so on. Because 1 over 2 to the power of n tends to get closer to 0 for n to approach infinity, then the limit of the equation is as shown on the screen. So, the genotypic probability of the offspring for n approaches infinity is En equals to A0 minus B0 plus C0 minus D0 plus E0 plus G0 minus I0, and also Bn, Cn, Dn, En, and so on are equal to 0. The equations that have been obtained can later be used to determine the probability of the nth generation in a population based on controlled crossbreeding.